Let us see the calculations at mass flow inlet now. For velocity, the velocity is specified as shown in this relation. For pressure, in case of supersonic inflow, the specified pressure is used. In case of subsonic flow, the boundary phase pressure is extrapolated from the adjacent cell using reconstruction gradients. Temperature. The static temperature is obtained from the specified total temperature using the isentropic definition of total enthalpy. Now we come to heat transfer modeling. First, we will have an overview of modeling capabilities when it comes to heat transfer modeling. Heat transfer is the study of energy in transit due to a temperature difference in a medium or between media. This transfer of heat takes place through three distinct modes of heat transfer: heat conduction, convective heat transfer, and thermal radiation. In most problems, heat transfer is coupled to fluid flow through convection and coupled to thermodynamics through fluid properties and phase change. Examples of fluid properties are density, material, conductivity, and fluid viscosity. Examples of phase change are condensation, evaporation, melting, and freezing. Therefore, from a modeling perspective, heat transfer must be seen as a multi-physics activity. StarCCM Plus provides additional models that let you create sophisticated simulations for specific applications. Boiling, where you are interested in modeling the improved heat transfer due to boiling and the creation of the vapor bubbles has little effect on the flow. Moisture boiling in solids, where you are interested in modeling the boiling of a moisture within a solid material. Thin film, where you are interested in simulating de-icing or defogging on a surface. Heat exchangers, heat transfer between two fluid streams, a hot and a cold stream, such as in radiators and air coolers. Heat conduction is the flow of internal energy from a region of higher temperature to a region of lower temperature by the interaction of the adjacent particles like atoms, molecules, ions, or electrons in the intervening space. This flow can be viewed as the transfer of energy from the more energetic particles to the less energetic particles of a substance due to the interactions between the particles. Conduction takes place in all forms of matter, solids, liquids, gases, and plasmas. In solids, heat conduction is due to the combination of vibrations of the molecules in a lattice and diffusion of free electrons. In gases and liquids, heat conduction is due to collisions between molecules and the diffusion of molecules during their random motion. Conduction is greater in solids because of the relatively closed fixed spatial relationships between atoms, whereas fluids and gases are less conductive due to the large distance between atoms. The law of heat conduction, also known as Fourier's law, provides a means of calculating the local heat flux. Thermal conductivities vary from material to material, being the largest for metallic solids, smaller for non-metallic solids, very small for liquids, and extremely small for gases. The major objective of performing a simulation that includes convective heat transfer is to determine the temperature field in a medium, taking into account the conditions that are imposed on the boundaries. The first law of thermodynamics and Fourier's law can be used to derive the heat diffusion equation. This is a second order partial differential equation in temperature or enthalpy or energy. From this, the temperature field can be calculated. This temperature solution can be steady, a function of space only and not changing with time, or unsteady. The temperature field varies in both space and time, as for example in metal quenching applications. Convective heat transfer is the transfer of thermal energy by the movement of a fluid. In engineering practice, it is used to provide specific temperature changes. Examples include heat exchangers, electronic device cooling, and cooling of turbine blades. Convective heat transfer comprises two mechanisms: energy transfer due to random molecular motion, that is diffusion, and energy transfer due to the larger scale bulk motion of the fluid, that is advection, which is the collective movement of groups of molecules. Convective heat transfer to or from a solid requires the transfer of heat by the bulk motion of the fluid and the transfer of heat by diffusion. The contribution due to random molecular motion dominates near the surface where the fluid velocity is slow. Convection is usually described as being either natural, that is free, or forced, although other mechanisms also exist. For example, gravitational, granular, thermomagnetic, capillary action driven, or Marangoni and Weissenberg driven effects. In a gravitational field, natural convection occurs due to temperature differences which affect the density and thus the relative buoyancy of the fluid. Denser components fall while lighter or less dense components rise, leading to bulk fluid movement. Natural convection is more likely and more rapid when any of these conditions apply. A great variation in density between two mixing fluids. A large acceleration due to gravity that drives the convection. A larger distance through the convecting medium. Natural convection is less likely and less rapid when any of these conditions apply. A more rapid diffusion, which acts to diffuse away the thermal gradient that causes the convection. A more viscous fluid. To quantify when natural convection is possible, the dimensionless Rayleigh number is defined and can be viewed as the ratio of buoyant and viscous forces times the ratio of momentum and thermal diffusivities.